Hey everybody, I've been wanting to give this talk for like 18 years, so this is awesome. I'm Mark LeBlanc. I am not at all related to this guy or this lady. This is me from 20 years ago, back before we could afford anti-aliasing or wardrobe. And this is from the credits for Thief, the Dark Project. So Thief was an immersive stealth sim. It didn't have it was a story-based game, but it didn't have a garden path for you to follow. You know, our idea was if we give you some interesting stealth tools and we give you an environment to use them and we give you some goals to achieve in that hopefully that improvisational fun would emerge from that, right? And so we very much approach it from the spirit of there's no such thing as an exploit, right? If we allowed you to do it, it was totally legit, right? So I'm going to talk about how we represented game entities in Thief, and by game entities, I'm talking about what you would think of, like all the things that are things in the game to the player, like furniture and weapons and people and ammunition and mounted heads on the wall, things like that. The individual things in the game world, right? What Unity calls game objects or Unreal calls actors, right? So to understand the sort of historical context in which we built the entity system for Thief, we have to sort of well, let's start by looking at the minimum spec for Thief. Okay, so it required a 200 megahertz Pentium, or if you had a 3D graphics card, which was not a given, you could go down to 166 megahertz. It required 32 megs of RAM, 60 megs of hard drive space, and it required a mouse, which, other than that requirement, this would run awesome on an iPhone 1. So this is the context we were working in, and keep in mind that like the machines that we were actually developing on weren't much better than what I just showed you, right? So that created this is what we were worried about. Compile times were a real issue for us, right? Like a small change on Thief took more than a minute to compile. Like the modern, sort of incremental compilation, incremental linking stuff was very, very new at the time. And so we had to think about that. Header editor dependencies obviously were a big deal for us because of the compile times, but also just because of, how to structure our app. Heap overhead. You know that every time you use the new operator or you call malloc, there's like 32 bits of like extra overhead just to keep track of, that allocation. And that was like huge for us. Heap fragmentation was actually a big deal. We could get into states where, we had enough memory, but it was, but the free blocks were all individually too small to allocate the block that we wanted. So in the early 90s, Looking Glass, which made Thief, was mostly working in DOS. I don't have time to fully explain this slide, unfortunately, but we were mostly working in DOS, and basically we didn't have virtual memory, right? So our approach to game entity was basically every game entity had a single fixed-sized memory block, probably around 128 bytes, to store all of its state. Right. I actually, in Ultima Underworld 2, I introduced a bug where if you throw an empty lantern against the wall, it would vanish because the byte that lanterns used to store their fuel supply was the same as the byte that other things used to store their hit points. And so my code, which was trying to do impact damage, right, was just looking at that byte. Oh, you have no hit points. I should destroy you, right? And of course, it has no destruction animation or assets or anything because it's a lantern that wasn't supposed to get destroyed. And so it just vanished, right? And so I had to I had to fix the bug by doing the check to make sure, are you the kind of thing that uses this byte for hit points as opposed to, for something else, right? Windows 95 was a huge deal for us. All of a sudden, first of all, we had a 32-bit address space, right? Before that, we were dealing with the growing pains of the Intel architecture, which really didn't contemplate you having more than a megabyte of memory, right? But now all of a sudden, you could address every single byte of your 32 bytes of RAM with a single address space, and that was a big deal. And we had virtual memory, right? And that made the fragmentation part more manageable. If you didn't have a block big enough, you could page out and get a new page, and now fragmentation is suddenly a performance problem rather than a correctness problem. Heap overhead was still an issue for us. So our aspirations, when we were building the Thief engine, right, we wanted to make sure that designers could do awesome stuff with it. We wanted to build this immersive sim, right? And we had really bad compile time, so we wanted to be able to do as much as possible between compiles, right? We didn't want to have to, if the designers wanted to change something, we didn't want to have to, deliver them a new build in order to have that change. And we needed to be kind to the heap, right? We needed to minimize that overhead and just be careful with our heap resources, right? So this is what we built. in response to those requirements. So the dark object system is what we called it, where entities are basically made of pieces like properties. So this is a first step towards, the modern, like, things are built out of components kind of architecture, right? We had a data-driven inheritance hierarchy. So the type database of different kinds of things in the world was completely data-driven and built by designers. And we actually had a system of first-class relationships between objects, links between objects, that was queryable. So in our context, in the dark object system, we called game entities objects, and we had some mandatory fields that every object had to have, right? Every object had to have an ID, and that's the end of the list. So an object literally was an integer, okay? And it had nothing attached to it. It's just an ID. And our minimum footprint for allocating an object was 12 bytes because you needed a link on the list of existent objects. And that was your overhead for making an object. So then, once you had that ID, we built up the object out of properties, right? So properties are values attached to objects, right? In our system, properties were data only. They were stateful, but they weren't class objects. They didn't have methods. They were really just records or individual plain old data types. And this is actually pretty similar to how Overwatch works, apparently, where objects are made of components that are pure state with no behavior, and then the game systems are pure behavior with no state. So in our case, properties were actually maps from object ID to value, right? And an ID could have a value or could not have a value, right? So again, objects aren't containers; they're just integers. It's the properties that are the containers of objects in some sense, right? So when you're accessing a property, instead of like taking the object and calling its get method with the hit points key, right? You're actually going to the hit points singleton and calling its get method with the object ID. And we had other APIs too. You could go to the hit points singleton and iterate over all things with hit points, for example. So this had some advantages for us. It had pretty good caching and paging behavior for the day. So one of the things is like games, if you had a game system like physics, right? If it's looking at the velocity of an object, it's not ever going to look at the hit points of that object. It's going to move on to the velocity of the next object, right? So it was pretty natural for us to keep all the velocities together, right, in one property. And if we chose the right data structures, we could keep all the velocities on the same page, or a bunch of velocities on the same page, and in some cases on the same cache line, right? And this allowed us to choose for each individual property. We could choose a different map implementation based on how we expected that property to perform. So, like if we thought a property was very sparse, then only a few things would have that property. Maybe it was just a linked list of pairs, but if it was something everything had, maybe we just had a big array indexed on object ID. So here's some code to create a property. It's been pointed out to me that I brought this into Visual Studio, and we probably didn't have the syntax highlighting back then that we have now. And basically the idea is, down here you can see create in property. Oh look, I got a laser. Oh no. You create in property, and it's a factory function that makes integer properties, and I'm going to pass it at this hit points descriptor, which is just a little form I can fill out describing what hit points is. And then I'm going to pick an implementation for it, right? So in this case, sparse hash. So this is the super generic, very common, simple case. If you were going to do something fancier, where you wanted your own map structure and you wanted a fancy record instead of just an integer, then you'd be in the realm of sort of making subclasses of the property implementation classes and stuff like that. This is all C++. So once you've invoked this code, and you store it in your little singleton variable here, I'm really worried now. You store it in your little singleton variable, and then you can call its get method to your heart's content. So once you've done that, what it looks like to the designer, right? So the designer can go in, and they can now add hit points to an object. Here I have a bystander, and it's got a bunch of properties, and I've added hit points to it, and I've set the value to 20. So we also supported inheritance. So an object could inherit properties from its species, essentially, from what we called its archetype, right? Archetypes were implemented as special first-class objects. They had IDs, essentially, that could have properties. And you can think of this as similar to like a JavaScript prototype chain, where like if we go to look for your hit points and you don't have hit points, we're going to ask your archetype for hit points, and then if we're going to ask your archetype's archetype, and we're going to keep going until we don't find it, or we do find it. And we cached that search at runtime. We pretty much knew what the type hierarchy was by the time you were playing the level, so we could cache the response of that, the result of that search, pretty with very little memory and pretty quickly. And our inheritance hierarchy was entirely built by designers in data. So once again, we have this bystander, right, that I showed you before, and you'll notice that the bottom thing on the tool is its archetype bystander, which is an object you'll notice has a negative ID because it's an archetype, and we can crack that open and we can kind of see what its properties are. Now note that this tool does not resize because we were too cool for that. So I have to scroll up, and now I can see what the properties of bystander are. I can see that bystander derives from human. And you can see all the, I get all these properties from being human. And for example, I get this air supply, which is how long I last underwater without taking damage. I believe that's milliseconds. So bystanders are pushovers by default. And you can see how the designer can see what properties are inherited from its archetypes. You can also edit the hierarchy looking top down, and so this is the actual hierarchy from Thief. I think it's technically Thief Gold, and so you can see that the bystander archetype isn't actually a leaf species. It actually has children, servant, and merchant, and actor. But you can see how this is what the designers built, and you can see how they used this tool to kind of express the actual typology, the actual taxonomy of things in the world. We also had this concept of meta properties. So meta properties were basically bags of properties that can be added to an object. So for example, if you wanted an object to be hairy, that might be representable as multiple properties. Like it might have visual properties of being hairy. It might change the way you sound to be hairy. It might change how flammable you are to be hairy. All of those things, right? So you could basically take all those ideas and you could take all those properties and you could put them in a bag and call that hairy, and then you can just add that to any object that you wanted. And hey, these meta properties are also special objects with negative object IDs that are in their separate hierarchy. So basically, we had multiple inheritance. Any object had one archetype, and it could have multiple meta properties. So and that could percolate up through the hierarchy. And because we had this duality of types, one is our relationship, and multiple has attribute relationships. That kept the sort of tangled dagginess of the inheritance graph under control. So designers so here on this tool you can see I have the animal archetype open up, and cold damaged, get KO gassed, and fire damaged are all meta properties, creatures and archetype, and then down below you can see creatures are all fleshy and solid, and physical is their archetype. So designers use them for AI capabilities. So if an AI could search for evidence, for example, or it could respond to dead bodies and look for a murderer, then that might be a meta property that they would attach to an AI that they placed in the world. They use meta properties for materials. So like if a thing was made of, here we have fleshy, if a thing was made of wood, or if it was made of metal, they would use meta properties to express those ideas. Vulnerabilities, gets KO gassed up there. That's a meta property that says, hey, I get damaged I get knocked out when I walk into knockout gas. And also status effects. Actually, when you did get knocked out, like you in the gameplay video, you saw a lot of guards get blackjacked in that video, right? When a guard gets blackjacked, we just add the knocked out meta property to the guard, and that just automatically overrides all of its behaviors so that it doesn't do anything. And that's how we did it at runtime. Eventually, we had this problem where we wanted to attach properties to terrain geometry, right? These same objects. We wanted to express that same idea for terrain geometry, but we couldn't really afford to have like an object ID per polygon in the world because that was crazy in 1998. So what we ended up doing is we had like one flyweight object per texture on the level, and so now all of a sudden like textures can have properties, right? So here's a texture called Planks 1, and you can see that it has the wooden meta property. And it belongs to the texture archetype. And you can see that one of the things it gets from the wooden meta property is the can attach attribute, which means that this is a thing that the player can attach a rope to. So here we have a rope attached. Can you see the rope attached to the ceiling? So anywhere the designer painted with this wooden texture, or with any texture that was considered wood, that was a place that the player could attach a rope to. Likewise, if they placed a tree in the world, that's just an object that also has the attach property, or a wooden shutter. That it didn't matter whether it was a train texture or whether it was an object. And this was a huge boon, particularly to our sound designers, who loved that they could just sort of talk about the interactions between materials explicitly. We also built a system for links, which are relationships between objects. So rather than, if you wanted to refer to another object, like say, for example, you're an AI and you want to know what things you're threatened by, rather than having a linked list of pointers to objects or IDs of objects that you're threatened by, you would have these sort of first-class links. Each link was a quadruple of the source. So me, I'm the flavor I'm threatened by, and the destination, that thing. And I could have some data attached to it, like how threatened I am by it, some scalar or some little record. So threatened by is an example of a flavor, or contains is an example of a flavor. You could query these links in either direction. So like if I made a threatened by link to some object, then I could query like, oh, tell me all the AIs that I am threatening, for example. You can query in either direction. They were auto-snapping, so if one of those two objects got deleted, got destroyed, then the link would just vanish. You didn't have to maintain your lists or anything. And like properties, you could kind of choose your map representation based on what queries you were expecting and what you needed to optimize. So here's actually that level that you saw in the gameplay video in the editing tool. And here is a visualization of all of the AI patrol links on that level. So the AI patrol routes are made using these links. And here is a representation of all the container relationships in the level. So what's this thing off on the left here? This is what designers called the green room. And this is like a place far off where they would put things like your starting inventory and other objects that just never needed to actually appear in the level. So those big links going from the level into, that's the spawn point linking to all your starting inventory, essentially. And because the container relationships didn't care about position in the engine, then the designers just laid things out so that things were easy to see. And that little tiny cluster here, this little tiny cluster right here, that I believe is the store. One of these is the store, and it links to all of the things that you can buy for your inventory before the game. The ones over here, I believe these are guards, and they're linking to like the weapons they're carrying. So that's all the container relationships. I can also just pull up a query of, this is all the links coming out of the spawn point, essentially. So you can see it's got a bunch of container links for what the stuff has. And it's interesting, the way you gave the player money is you like put a purse in his inventory that was worth however much you wanted him to have. The other thing you just notice, they have this player factory link. And notice this has a negative object ID because it's pointing at the archetype of the player, right? Garrett was our character in Thief. So that was how you said this is what kind of thing you're going to spawn at this spawn point is. So here are some things that we discovered along the way of making this. First of all, we couldn't afford to store things as like JSON or XML or anything like that because we didn't have any disk space, right? So all of this stuff was binary files, right? This is the brain. This is a Nerf brain football. This is not the actual brain from Thief. This is just a picture I found on the internet. But this was the physical semaphore that the designers used in order to control who could edit the object hierarchy, who could edit the type hierarchy of objects. So if you wanted to make a change to all humans, you had to like find the designer who was currently editing the object hierarchy and ask him to give you the brain so that you could check in a change to that. That was pretty challenging. So one of the things that we really didn't support well is the distinction between configuration and state, right? So what I'm talking about is the difference between sort of immutable data that can be shared amongst a lot of things, right? So for example, in a lot of games, if you have physics, then the mass of an object's going to be an immutable fact, unless you're making Smash Brothers or Kerbal Space Program. The mass of an object is probably going to be the same, and so the mass of every guard can share the same mass. Right? Whereas the velocity of an object is something that is a high frequency state thing that the object needs. And you often need to iterate, right? If I have velocity, then that probably means I might want to iterate over all the objects with velocity, right? And we didn't really have a good answer for, we had answers for each of these things, but we didn't have a good thematized, separation of configuration and state. It was all very ad hoc. And often a game system like physics would need both. And it would have been nice to be able to like have some abstraction that like lets you tie your configuration together with your state. You need some of each, yeah. We didn't have really a good separation of model versus view. So separating the logical state from the visual state of an object. So there was a bug in Thief where you killed a guard, and while it was playing its death animation, it would see its own dead body and shout, "Oh my God, there's been a murder!" And if we had, and that was because the visual state of the guard was still dying, but the logical state of the guard should have been already dead, and because we didn't have that good separation, we had that kind of bug. Lots of if you want funny bug stories from Thief, just come after, and I'll tell you a zillion. Moore's Law kind of turned out to be our frenemy. Like Windows 95 and having 32, oh my God, 32 megs of RAM, gave us all of this opportunity to build all this cool stuff, but it also moved the goalpost, right? All that cool stuff became expected. Lastly, players are awesome. This entire talk was made possible by the Thief mod community, which has been maintaining those tools on into the 21st century. I just went everything you saw there was downloaded from the internet. I couldn't get my own stuff to run. Like literally, I had to go to the fan installers to get the tools to install. So ttlg.com and silac.net were valuable resources for me. And the gameplay video was done by this guy Zevik, who does gameplay videos of everything apparently, and is apparently really good at playing everything. Anyway, that's it. And if you have any questions, I'll take them now. And you can also hit me up on Slack or email.